I took a fateful step very recently. I started a company to try to make this vision come true along with my partner Kirk Dorius, and so we're going to be introducing Flibe Energy to you today, a new company and one devoted to making thorium a reality. Let me start out with one of my favorite quotes from a writer for Newsweek. We Americans want it all: endless and secure energy supplies, low prices, no pollution, less global warming, no new power plants or oil or gas drilling either, near people or pristine places. This is a wonderful wish list whose only shortcoming is the minor inconvenience of massive inconsistency. Now, Mr. Samuelson wrote this in 2005, and I immediately wrote him an email, and I started talking about thorium, and he said, never heard of it. And I kept pressing on him, and on my birthday in 2005, he wrote a very small piece in Newsweek saying, well, somebody wrote me about thorium, and it sounds really interesting, but, you know, who knows? We'll see. A few years later, I had the good fortune to meet Ambassador Woolsey, who used to be the director of the Central Intelligence Agency, and I love this quote from him. If you want to know who's paying for the hate to be taught, next time you pull up to the pump, look in the mirror. Thanks to Colonel Rogi's excellent presentation, we understand the seriousness of that challenge. Another quote I love because I hate it. We do not have the resource base to be energy independent. The fact is the Middle East and the rest of the world will have to depend increasingly for its oil and also for its natural gas from the Middle East is not a matter of ideology and politics. It is simply inevitable. No, sir, it's not. No, sir, it's not. Another gentleman I've had the good fortune to sit down with, Peter Thiel of Clarion Capital. If you ever see the Facebook movie, he was the guy that put up the money. Technology entrepreneurs and investors would do well to return to hard and important problems. Not that, you know, building Farmville on Facebook isn't important, but, you know, we would do well to start working on the real problems. So, taking Mr. Thiel's advice to heart, we started a company with these value propositions. Energy independence is possible. Yes, Mr. Raymond, it is possible, and it's affordable. But the key is something that has been almost uniformly overlooked by policymakers: thorium. And of course, in this room, we're hearing it, but we have to appreciate how little we hear about it outside of gatherings like this. We almost hear about it not at all. The machine is the liquid fluoride thorium reactor, which is safe and mechanically simple. And when we set out to build lifters, we will not only produce electrical energy, but we will recover valuable medical radioisotopes that can provide an early financial return. We want to generate electricity. We want to desalinate water, and we want to make these radioisotopes not only for the medical sector, but also for NASA. I spent 10 years at NASA, and they are in a terrible world of hurt right now to produce a key material they need to explore the outer solar system. We saw this chart thanks to Colonel Rogi, so just remember we're the little bitty thing up there in the left-hand corner. Most of us are familiar with the thorium fuel cycle, but the basic principle is thorium has the ability to be consumed if you are careful with your use of neutrons. If you are prudent with your neutron budget, you can continue to consume thorium so long as you have a fissile starter, of which uranium-233 is the best. Thorium, of course, is not uncommon, and there are particular places in the United States where it is exceptionally common. But Flibe, which is where we derive the name of our company, is really the secret to unlocking thorium's potential. And I was very glad that Raluca was talking a little bit about Flibe and the experiments they're doing at UC Berkeley. This is a picture of Flibe with uranium tetrafluoride in it. It looks like blue rocks when it's crystallized. It looks like palm olive when it's liquid. Flows like water. Very hot, but chemically stable. This was taken back at Oak Ridge a long time ago. Nuclear reactors based on Flibe were really built and operated. The molten salt reactor experiment was successfully operated using Flibe salts for 4 years at Oak Ridge National Labs. Much of the Flibe is still there. A couple of years ago, we tried to see if we could get a hold of it before they threw it away, but Oak Ridge has now taken possession of it, as long as it's in good hands. I just didn't want to get thrown away. How do we use this thing? Let me walk you through our plans to utilize thorium in a Flibe reactor. This is not the way the core really looks. This is a cartoon to make things simple. The fuel salt, which is a lithium, beryllium, uranium fluoride salt, enters the core region where there is moderator material, graphite, we're anticipating, to slow down the neutrons, create a thermal spectrum reactor, and to sustain criticality. Now, as that core fluid moves out of the reactor, it's hot and fission stops. About half the neutrons in the core are sustaining the criticality of the reactor. What I mean by that is one fission is causing another fission. That's the basic definition of criticality. About the other half of the neutrons are making their way out of the core into this blanket region represented in blue, and that's where the magic happens with thorium. This is a Flibe salt, lithium, beryllium, thorium fluoride. Thorium's great at absorbing neutrons, it's great at absorbing gammas, and it's just what we want to have absorb those neutrons so we can make new fuel. Small amounts of uranium tetrafluoride will begin to form in the blanket, and they can be extracted through a simple chemical process of fluoride volatility. This is where you expose the blanket salt to a small amount of a fluorinating agent, either a fluorine gas, perhaps nitrogen trifluoride. The basic principle is, because thorium is tetravalent, and only tetravalent, and uranium has multiple valent states, that's a very easy chemical way to separate it. So out will come uranium hexafluoride as a gas, and then you want to introduce it into the fuel salt. So you have a stream of fuel salt that will enter the reduction column. By exposing UF6, hydrogen gas, and fuel salt together, you can get the hydrogen to go whoosh, whoosh, to two of those fluorines, stealing them from the UF6, and reducing the UF6 back to UF4, which is now in solution and goes back in the core. So the core is being continuously refueled from the fuel that is being generated in the blanket. In turn, the core is generating new fuel by neutron absorption in the blanket. Another great thing about this blanket is the fact that it's basically your primary neutron shield. A two-fluid reactor becomes a very scalable reactor in size. You can build them big, you can build them small, and the whole secret is that thorium blanket, so good at capturing neutrons. The hydrogen fluoride you produce in this can then be electrolyzed to regenerate your initial component. So this is how we move fuel from the blanket into the core salt. A little bit of mention has been made to an emergency denaturing system. If for some reason we need to trash the isotopics of the core, we can do that very quickly. I would just as soon keep U-238 out of the core because I don't want to make plutonium. But if we need to do emergency denaturing, we can. Okay, in the core, we're sustaining these fission reactions. We're producing fission products. Perhaps periodically, perhaps continuously, we need to reprocess this core salt. That also takes place through a fluoride volatility process that will convert UF4 to UF6. We separate out the different hexafluorides. We put UF6 back into the core. All right, zooming out, so to speak, my favorite part, the mechanical engineering. Hot salt comes out of the core. It gives up its heat in a heat exchanger to a coolant salt. It could be bare Flibe, it could be Flynac, different salt possibilities. And then that gives up its heat to a hot gas that runs through. This is an extremely simplified version of our gas turbine. In reality, it's probably got multiple stages and regenerators and so forth, but this is a super simple version. The gas is heated, it runs through the turbine, it's expanded, the gas emerges from the turbine, actually really goes into a regenerator, and then is cooled in a gas cooler before being introduced into the compressor. It is then repressurized and introduced again back into the regenerator and then into the heater. This spinning turbine, about half the power it makes turns the compressor, the other half turns the generator, producing power for the grid. The significance of the gas turbine is we can hit high efficiencies with a gas turbine. Water is not a good working fluid, a steam turbine, for this kind of technology. This kind of technology is going to be operating up in the 1000 K temperature range. Way beyond where we go with water. That's what enables you to hit up in that 50% conversion efficiency. That reduces the amount of heat you're going to have to reject to the environment. Even more significantly, the heat you are going to reject to the environment can then be used for desalinization. When we condense steam right now at a relatively low temperature, we can't use that effectively for desalinization. As we cool a gas, as it drops from about 100 C to about 30 C, we can drive a desalinization system with that. And Dr. Per Peterson's done some great work looking at how we couple gas turbines to desalinization systems. Another compelling product that can be generated from this technology. But mainly, we're out to make electricity, we're out to run the grid. When we want to run a pressurized water reactor today for a year, it takes about 250 tons of natural uranium. We enrich it, we put it in the reactor, we expose it for a while. We burn up most of the U-235 in it, make some plutonium, make some fission products, but most of it's still unburned fuel. And we take it out because the fuel has sustained radiation damage. It's cracking, it's swelling, it's not going to stay in there any longer. Plus, it's not breeding enough fissile to continue its consumption. We don't make more fuel than we consume. On the other hand, in a lifter, we introduce thorium into the blanket, as I mentioned earlier, and the end product is a ton of fission products. We keep the transuranics and the actinides out of the waste stream, and that's very significant from a waste disposal perspective because that's what drives your waste disposal criteria. These fission products are decaying quickly. not even within 10 years, within just a few months, two of the most important ones, xenon and neodymium, are both stable and can be partitioned and sold. At NASA, we love xenon because we use it to explore the outer solar system and run ion engines on it. When I made this chart, I said, well, this is the real waste. Actually, I've come to think, in a lot of ways, the remaining fission products could still be extremely useful. We've been talking about passive safety in the lifter community for a very long time. After Fukushima, a lot of people started to pay much greater attention to this aspect of the reactor, but we are no Johnny-come-lately to this. In fact, this was all come up with long before I was ever even born. This was demonstrated back in the 60s with the molten salt reactor experiment. The whole idea of using this liquid salt, having a freeze plug where a blower would freeze a plug of salt in the line. If you lose all power, that freeze plug will melt, the salt will drain into a drain tank where now passive approach to decay heat removal, you're maximizing heat transfer to the environment, whereas you're trying to minimize it in this reactor. It's a reactor that can downshift fundamentally to a completely different mode and achieve a staggeringly impressive level of safety, even if there's physical damage to the reactor. See that catch pan? Everything is there to direct the fuel into the drain tank and into a passively cooled configuration. We can't say enough about this feature, and it is unique to liquid-fueled reactors, and particularly unique to liquid-fueled reactors that have elevated melting temperatures. So even though we have to get the salt hot before it melts, that's the very feature that makes the freeze plug and drain tank work. So there's goods and bads with all of this. We talk about medical radioisotopes for a little bit because this is an important aspect. I've mentioned molybdenum-99. Let me talk about bismuth-213. There's 4 natural decay chains of alpha-emitting radioisotopes. One starts with U-238, U-235, Thorium-232, and then there's one that's extinct because it has no long-lived precursors on it. It was there in the supernova billions of years ago. It's gone now, and it is on the U-233 decay chain. There is a special product on there, bismuth-213, that could be a smart bomb against cancer. They attach the bismuth-213 to an antibody. It seeks out the cancer cell, binds to it, and that alpha emitter delivers a knockout blow to the cancer cell. This is a very, very targeted application of radiopharmaceuticals. I know we have 2 radiation oncologists in the room today, so forgive me if I'm not describing this quite right, but I sometimes even lay in bed thinking, if my kid had leukemia, how hard would I be working on getting this therapy ready for them to save lives? And if it's that important, why aren't I going full bore on it right now? This is a great technique against dispersed cancers. And again, I hope I don't get out of my lane here. But from what I understand, if you've got a dispersed cancer, this is the approach you want to take to go after it. And there's only one way to get this material. There's a uranium-233 inventory at Oak Ridge. We need it to start lifters, and we also need it to go and extract this life-saving medical radioisotope. So remember, bismuth-213. People have known about it for a long time. Look at the time on this report, March 2001. Actinium and bismuth-213 are currently extracted from purified thorium-229. And the real trick here is to remember, every time you have an alpha decay, that number goes down by 4. So 233 minus 4 is 229. So all these guys are on the same decay chain. The only practical way is to get this from the natural decay of thorium-229, and it is only produced from the natural decay of 233. It's very potent. We only need on the order of 1/1000th of a gram to treat a patient. We need to go get this stuff, and we will do it in the course of making lifter a reality. Another thing near and dear to my heart after time at NASA, these radioisotope thermoelectric generators are based on plutonium-238, and this is the only way that we've been able to explore the outer solar system. The United States is unique, the only country in the world that has sent space probes beyond the asteroid belt, and it's all been based on having this technology. Short answer, we're out of the stuff. It's gone. We've used it all up. The Russians used to sell us some. They've sold us all their inventory. It's gone. NASA's got billions of dollars of deep space missions hinging on having enough of this stuff to run the batteries to let the thing call home. We will be able to make this in lifter. If you've heard sometimes about us saying we burn up 99% of the fuel and there's 1% left, the 1% left is that stuff. And it's worth almost as much as the stuff we burn up. Again, recognized in National Research Council reports that we've got to restart domestic production of plutonium-238. The United States has delayed action. The situation has become critical, no pun intended. Continued inaction will exacerbate the magnitude and impact of these shortfalls, causing them to eliminate missions until a source of plutonium-238 is developed. This was written a couple years ago. This is happening right now. NASA is cutting back on their plans to explore deep space because they don't have this stuff. So what could we generate from our cornucopia of material from the lifter? 1,000 kilograms of uranium-233 would be worth hundreds of millions of dollars of electrical sales as we fission and generate electricity. Even as we peter this out to the point where 1,000 kilograms of this will end up with 15 kilograms of plutonium-238, NASA will love that. They'll go bananas if we can get 15 kilograms of U-238 for them. Along the way, we'll make 20 kilograms of medical molybdenum-99, thorium-229 for targeted alpha therapy treatments, 20 kilograms of radiostrontium that can be used in remote heating units, and 150 kilograms of stable xenon, 125 kilograms of stable neodymium. Now, these aren't worth all that much money, a couple $100,000, but they'll pay for the 1,000 kilograms of thorium that did all this trick. So, out of this marvelous machine comes a variety of different revenue streams, each of which has got a community that is literally begging for them. We are unique in our ability with the lifter to make molybdenum-99 in an operating power reactor. A solid fuel reactor would have to shut down and try to take its fuel out of a process to do it. We don't have to do that. We can make it while we're operating. We also don't have to make plutonium-238 in the expensive way. Until very recently, I was Chief Nuclear Technologist at Teledyne Brown Engineering. Had a fantastic time there. Really loved working with them and really loved getting the paycheck every 2 weeks, too. That was great. So it was a big moment to go out and do Flibe. Previous to that, I was on assignment from NASA to the Army Space and Missile Defense Command for 2 years. Had the privilege of meeting people like Colonel Rogie, others of our men and women in uniform. I also gained a lot of insight into the challenge that our troops face, not only in combat regions, but also in remote sites like Kwajalein Atoll, Fort Greely, Alaska. We have a real need for remote power systems, and Colonel Rogie did such a good job describing that, I won't go into any more detail. At Marshall Space Flight Center, I've been working on a nuclear engineering degree. My very long-suffering professor is here in the audience. Thank you, sir. I will graduate one of these days. Previous to that, got my aerospace engineering degree from Georgia Tech. I want to introduce my partner, Kirk Dorius. We were both graduates of Utah State University and friends there, and he went on to pursue a lucrative career in the law profession.
So briefly...
we're not done.
Oh, we're not done. So briefly, Kirk and I have known each other for about 20 years. We started engineering together in the early 90s, and after we parted ways at the end of engineering program, I went on to work at Boeing, studied patent law at the University of New Hampshire, including a stint at Tsinghua Law School in Beijing, studying international patent policy and law. Although we have only recently incorporated, we are actively pursuing strategic industry and research partnerships. We have an ambitious development program to at least have demonstration criticality in June 2015, the 50th anniversary of when the Oak Ridge National Lab reactor went critical. And to address some of John's comments about the likelihood of the United States capturing this intellectual property and commercializing lifter. Intellectual property is one of my main hats I'm wearing for Flibe Energy, along with business development and engineering. And to address Rusty, I will keep him out of trouble on export control as well. And we have plenty to do. We're working on it. And we'd like to give you our first mainstream media introduction to Flibe Energy.
Thank you so much, Kirk.